Hello students, I'll be teaching you some topics in your physics course. Myself Dr. Koel Ganguly, I am an associate professor in physics at Institute of Engineering and Management, Kolkata. I'll be teaching you the topic blackbody radiation in quantum physics. So my lecture plan is as follows. At first I will give you a brief introduction about the absorption and emission of radiation by any object at any given temperature. Then I will talk about the emissive power and absorptive power of an object. Then we will discuss the Kirchhoff's law of radiation. Then I will give you an idea of what is meant by a perfect black body. And at last we will talk about some examples of black body. All of you must be knowing that when radiation is incident on a surface, a part of the radiation gets reflected back into the same medium and a part gets transmitted into the other medium, and some portion of the radiation is absorbed by the surface. As the surface absorbs this radiation, it can also emit the radiation. The emission of radiation by an object that depends on the temperature of the object. If the object is of a low temperature, then it will emit less amount of radiation, and if the object is of a high temperature, then it will emit more amount of radiation. The emission of radiation of an object will consist of all wavelengths at a particular temperature. Some wavelengths will be emitted more and some wavelengths will be emitted less. So we can say that any object at any temperature is known to emit thermal radiation. And the characteristics of this radiation depends on the temperature of the object and also on the surface properties. If the surface area of the object is large, then more amount of radiation will be emitted. If the surface area is less, then less amount of radiation will be emitted. And this thermal radiation consists of a continuous distribution of wavelengths from all portions of the electromagnetic spectrum. So I will give you one example. If we heat an iron rod, then the rod first glows red, then yellow, then blue, and then it glows white at a very high temperature. So as the temperature increases, the wavelength of the radiation decreases. Another such example is if we heat some charcoal, then the color of the light emitted by the charcoal that will depend upon the temperature. Now a question can arise in your mind that we are saying that all possible wavelengths are being emitted, then why is it that we are seeing only the red color or the yellow color or the blue color and not all the colors? This is because some wavelengths are emitted more and some wavelengths are emitted less, and our eyes can perceive only those wavelengths that are emitted more. Another question might also can come in your mind that we say that any object at any temperature can emit radiation. Then we see so many objects around us in our room like the table, chair, almirah, or even so many objects in our surroundings. Does this mean that all these objects emit radiation? Yes, they do emit radiation, but the wavelength of that radiation should be in the visible range for our eyes to perceive it. If the wavelength of the radiation is of a higher range like in the infrared region or in the lower range like the ultraviolet region, then our eyes cannot perceive the radiation. Now I will talk about the emissive power of an object. So the emissive power of an object is denoted by E lambda, and at a given temperature T and wavelength lambda, it is defined as the energy that is radiated into vacuum per second per unit area per unit range of wavelength. Now let me talk about the absorptive power of an object. The absorptive power of an object is denoted by A lambda, and that is defined as a ratio of the amount of energy absorbed by the object to the amount of energy incident on it. Now let's state the Kirchhoff's law of radiation. So Kirchhoff's law of radiation states that the ratio of the emissive power to the absorptive power of a body at any temperature and wavelength is a constant. So E lambda by A lambda is a constant. So higher the value of E lambda, more should be the value of A lambda for the ratio to remain constant. This signifies that a body having high emissive power will have a high absorptive power also. So a body which is a good emitter will also be a good absorber and a bad reflector. Now let me tell you what is meant by a black body. So a black body is a body that can absorb all radiation that is incident on it. So for a perfect black body, the emissive power E lambda and the absorptive power A lambda is 1. So a perfect black body is a perfect emitter and a perfect absorber. Now this means that whatever radiation is incident on a black body, it absorbs all the radiation and it emits all the radiation. So this means that it does not reflect or transmit any of the radiation. So this indicates zero reflection and zero transmission for a perfect black body. And all these implications are true for all wavelengths and all incident radiations. So how a black body spectrum will look like? So it will be like an electromagnetic spectrum consisting of radiations in the lower wavelength region like the gamma rays, X-rays, ultraviolet rays, and also radiation in the high wavelength region like the infrared rays, radio waves, and definitely there will be radiation in the visible region also. Now let me give you some examples of black body. So hot molten lava is a good example of black body. The hot iron rod, which already have discussed, is an example of black body. Our stars and planets are considered to be good approximators of black body. So our sun, which is a star, can absorb most of the radiation and emit most of the radiation. Our planet Earth can absorb most of the solar radiation and emit most of them. So these are some of the examples of black body. Now with this I have come to the end of this lecture. Now in the next lecture I will teach you how to design a black body in the laboratory, and then we will do experimental study of the black body spectrum, and we will also discuss the Wien's displacement law and the Stefan Boltzmann law. Thank you.